Drake, can you read me the title of this lesson? Yeah, I got that part. The title. Keep going. Orbital what? Again, not to make fun of you. Orbital what? Wait a minute, Mr. Dewick. Isn't potential energy just mgh? Well, there's a problem. As you go further and further away from Earth, what happens to that value there, the 9.8? What happens to it as you go further from Earth? Okay, we need to give you a new way to calculate potential energy on a cosmic scale. That's the theme of today's lesson. And that means a lot of our conservation of energy equations, we're going to transform them slightly, Sarah, into cosmic potential energy, okay? Recall, I wrote. So this is the problem we have to deal with. We're going to try and derive it. The area under a force versus distance graph. What was the area under a force versus distance graph? Yeah, the letter W. Yeah, it's work. But I'm going to be a bit more specific. So let's label this F. Let's label this D. Here's our graph. Just draw kind of a line slanting up. This is a changing force. The force is increasing, so you wouldn't be able to just go force times distance. You'd have to use the area. And then what I'd like you to do right about here, put a point A. Right about here, put a point B. And then you can extend the lines up. Sketch that. The area under a force versus distance graph is work, but if I wanted to be more specific, the area here is the work required to move some object, I don't know what it is, from point A to point B, from location A to location B. If I'm going to be really fussy, that's really what we're talking about. How much energy, how much work it took to move that object from location A to location B. If we graph gravitational force versus separation distance r, so this is still a force versus distance graph, Andy, but I'm going to use r because r was in our gravitation formula. Now, first of all, don't write this down. This is just for nerdishness. Well, we'll write this down. What is the equation for the universal force of gravitation? Big G, what is it? This is really similar. This looks like this graph here. Y equals 1 over x squared, because there's an r squared on the bottom, and r is sitting where the x is. This is a, have you guys done reciprocal functions in math yet? It's a reciprocal of a parabola, because x squared is our good old parabola. If you flip it, it's a reciprocal of a parabola. It's going to look like this. Trust me, don't believe me, you can try graphing, if you have a graphing calculator, 1 over x squared, and you'll see it looks kind of like that. So now I'm going to talk, how about right here, let's put a point R0, our starting radius, our starting location, our starting distance from the center of the planet. See how we're working in some cosmic stuff here? Let's put a point right here, R final. We get that. Is that okay? Let's redraw this graph in a bit more detail. So let's put FG right here, R radius, distance from the center of the planet right here. Let's do one specifically for Earth. As a shape, because it's based on the reciprocal of a parabola. You know what? Hang on. It looks like I'm tilting up at the very end there. It's asymptotic. It's always getting closer to zero, never quite touching zero, and it's shoots off to infinity, never touches infinity on the y-axis. Calculus students, there's some limits at play here if you want to be fussy. Let's put our Earth right there. Let's put our orbital right there. If you want to figure out how much rocket fuel, how much energy, how much work it's going to take to get whatever object you want up to that high, because G, the 9.8, is changing constantly, here the area is how much work, and you can put in brackets energy, to lift object from Earth's surface. That's our Earth, that's the surface of the Earth, that's where we start, to orbit, whatever your orbital radius that you desire, Rebecca, happens to be. And we've already said, well, you want to know what the orbital radius is? Tell me what you want the speed, or usually it's tell me what you want the period to be, and I can tell you how high we need to get it. Okay? There's a problem. We don't know how to find the area under a curve. Who's my calculus students here? Somewhere around, I'm going to guess, end of April, beginning of May, you'll learn something called the antiderivative, which is going backwards. It's when we give you the derivative and say what function did it originally come from, and it turns out that's actually going to also be the equation for the area under a curve. So you find the equation for the area under a curve by being given the derivative and reversing the procedure. You add 1 to the exponent, and then you divide by the coefficient instead of timesing by the and stuff like that. But for now, I have to do some bad, incorrect math to get the correct equation. So I'm going to do a proof. This proof is technically, Connor, mathematically not valid, but it ends me up in the right place, so I'm going to take it. Since work is force times distance, we can say, instead of work, I'm going to say potential energy is gravitational force times radius. Which is going to be big G, big M, little m over r squared times r. Oh. Yeah, one of the r's cancels. And so this gives us our equation for cosmic potential energy. PE equals, leave a space, we're going to add something in just a second, but it's big G, big M, little m, not over r squared, just over r. But here's, Nick, what we have to add. It's negative. Where'd the negative come from? Okay. Who's my calculus students? Okay. The negative comes from the fact that if you take the derivative of potential energy, you have to get force. And the only way that that works is if you start with a negative in the equation. Trust me, with respect to r. Try it sometime if you're bored. So take the derivative of this equation with respect to r. You can make that a little r to the -1. That -1 would move to the front. You want it to cancel with that negative, so you get a positive force. I can say that to my calculus students, but I lost my non-calculus students. There's another explanation. Okay? Out at infinity, at the edge of the universe, I'd like you to imagine that we went to the edge of the universe, so we were infinitely away from any planets. There's no gravity acting on us. If there's no gravity acting on us, will we fall? Will we fall if there's no gravity acting on us? So if we won't fall, How much potential energy do we have? 0. Okay? Out at the edge of the universe, you have 0 potential energy. In fact, this is how we're going to define it. We say, the phrase we say is relative to 0 at infinity. Sometimes you'll see me, I'll abbreviate that, but relative to 0 at infinity. So out at the edge of the universe, how much energy do I have potentially? 0, because I won't fall. With me so far, Drake? However, to get there, I would have to do work. I would have to burn fuel. I would have to add energy. If I'm adding energy and I end up at 0, what numbers must I have started with if I add something and end up at 0? Have to have started with negative. What numbers are less than 0 potential energy? Negative. We use the phrase relative to 0 at infinity. I think in the homework sometimes you'll see me abbreviate as relative to 0 at infinity. I'll abbreviate it as RTZAI. When we're talking about cosmic potential energy, Kayla, we had to put 0 somewhere, and putting 0 on the surface of the Earth would have been egotistical and very location specific. No, if we're going to go cosmic, you know where 0 potential energy actually is? It's out at the edge of the universe. And since we have to burn fuel to get there, we have to do work to get there, we have to add energy to get there, I guess we're all negative. Now, trust me, all the physics, everything that I've taught you will still work. If you know you're supposed to get a positive answer, you'll end up in your equation with a minus somewhere along the way. Trust me, it'll all work out. But you just have to raise your level of cautiousness, of carefulness, of just don't blindly plug and chug, Drake. Really think about things. Example 1. A 3,400 kilogram mass is released from a height of 6,300 kilometers above the Earth. How fast will it be going when it hits the ground? What does this question want me to find? Oh, ignore air resistance, because I've told you air resistance is a bear. Anyways, what does this question want me to find? VF. You ready? Is there a change in height? Is there a change in speed? Yes. Is there a yucky, curvy graph? This is a job for conservation of energy. So now I'm even broadening that a little bit. You ready? Are any of these 0? It's no longer 0 when you hit the Earth, so we can't cross off PE final. Prince Edward Island finally rears its head in pride and says, yes, I get to stay. 0 would only be Jocelyn if we start out at infinity, or our euphemism for infinity, or euphemism if we teach in the US, sorry, Trump joke. If I say starts from a really far distance away, that's my way of saying you can assume it started with so little energy that it essentially has 0. Okay? I think we can say, though, since it says released, we started at rest. You okay with that, Max, when you're done yawning? Yes? Yeah. If you show up on time, don't yawn. Max, are we in outer space? Are we cosmic here? Say yes. The most common mistake, and unfortunately, folks, I'll give you 0 for the rest of the question. Don't write this down. Kids go, oh. Why can't I do that, Drake? Because up there, G is not 9.8. It's smaller. In fact, G will be constantly changing as this object falls. I need the cosmic version of potential energy, which is negative big G, big M, little m, over R initial. This is the only other equation on your formula sheet in this unit. That one there. Kinetic energy is not going to change at all. So kinetic energy is still what? Half m, and I guess this will be V final squared. Plus, we're still cosmic. Aren't we on the Earth? We're cosmic, so we cannot use MGH. Negative big G, big M, little m, over R final. Over here in the margin, we're just going to list a little bit of data. What's R final? Okay, it's going to be the in this case, it's going to be the surface of the Earth. By the way, if you're launching something from the surface of the Earth, our initial will be the 6.38 times 10. Okay. What's our initial? Well, here's our key phrase. Please notice it's kilometers above the Earth. So it's going to be 6.3. Can you multiply that by 1,000? Do you get 6.3 times 10 to the 7th? Double check me. Or 10 to the 6th. Better double check, Mr. Duke. 10 to the 6th. Right? Okay. 6.3 times 10 to the 6th. That's the altitude. I'm going to have to add the radius of the Earth. That gives me the total distance from the center of the Earth where we dropped this object from. Julie, okay with that? It's because I gave you an altitude here, and we talked about that last class. If we're above the Earth, you've got to add the Earth's radius in as well. So our initial is going to be what? 1.268 times 10. Okay. Let's go back to our equation. Oh, I noticed one thing. How big the mass is won't change how fast it hits. It'll change how much damage it does, but not how fast it hits. What am I trying to find? VF. This is right around where my love for getting things by itself starts to reach its limit. I'm not going to blatantly get the VF by itself. I'm going to plus this to that side first. Negative big G, big M over R initial plus big G, big M over R final. That equals 0.5 VF squared. I'm going to not get the VF by itself. I'm going to calculate the whole left side, and eventually, once I have the whole left side, then I'll divide by 0.5 square root, because that I can do as a final step. We've done that a zillion times. But this is going to be some heavy-duty plug and chug. I'm going to give you a little bit of advice. Put your calculator down, Duncan. Negative, what's big G? What's big M? Since we're on the Earth. What's R initial? 1.268 times 10 to the 7th. Plus, here's my first bit of advice. Do you notice that these two expressions are quite repetitive? Ditto mark times ditto mark. I'll let you do that in your work, because honestly, I think that'll cut down on your mistakes, because we're writing such complicated expressions. I always see typos, or the equivalent of handwriting typos, show up in kids' work. Ditto marks you're not going to butcher. Divided by 6.38 times 10 to the 6th. That equals 0.5 V final squared. And now I'd like all of you to get your calculators out, but hold on. Get them out. By far, the most common mistakes I see here, Kayla, are calculator typos. I'll tell you right now, 90% of the time when kids come in, Mr. Dewick, I can't get the right answer. And then when I sit next to them and stare at them and help them type it in, they get the right answer. And I say, you made a calculator typo. I want to minimize my typing. So I didn't say start typing yet, Duncan. Trust me. Only type in the first expression. Negative 6.67 scientific notation button negative 11 times 5.98 scientific notation button 24th divided by 1.268 scientific notation button 7. Only type that in. And see if you get negative 3145639.15. So do that. Everybody got that okay? I'm going to write that answer down underneath the first expression, and I'll carry it to 5 or 6 or 7 sig figs. Julie, did you get that okay? Kayla still typing? Okay. No, this is, hey, I'm telling you, I told you, by the way, the physics and the math, the physics of what I show you is not going to be that complicated. The holy smokes typing of what I'm going to be doing today is off the charts. So I'm going to write down negative 3145639.09. I'm going to write a plus sign. I found the fastest way to do this, the best way to do this, and the way that reduces the least errors is now to just backspace and edit, because I just want to delete the negative. Yes? And I just want to change the radius on the bottom, but everything else is going to stay where it is. 6.38, scientific notation button 6, delete that. And I get 6251818.2. That equals 0.5 VF squared. By the way, if like me you're extraordinarily lazy, instead of deleting the negative, because that requires you to backspace all the way to the beginning, you can also just multiply your answer by negative 1 to get rid of the negative if you're that lazy. Have you got that answer now on your screen? Yeah. So I want to go that number plus negative 3145639. That's the left-hand side of the equation. And now get the V by itself. How would I get the V by itself? Divide by 0.5. That gives me a V squared. And now, boys and girls, how to get rid of a squared? Square root. It's going to hit the ground pretty fast. Yeah, meteors hit the ground pretty fast. 7, 8, 80. Turn the page. All we're going to, by the way, I've done the whole lesson. All I'm going to be doing now is showing you ways that we can incorporate our cosmic potential energy equation. Nevada, what does example 2 want me to find? Third word. How much work? Okay. Why can't, don't write this down, why can't I just go work equals the force of gravity times distance? Because as you leave the Earth, what happens to the force of gravity? It's a changing force. This equation does not work. No pun intended. I could find the area under a graph. No, wait a minute. We already saw it. That graph's a curve. We don't have the mathematical skills to handle that. So we have to go to the work energy theorem, our third definition of work. And this is why all those weeks ago, I actually allowed you to add this equation to your formula sheet. You're the first group I've allowed to add this equation to your formula sheet. What's the final definition of work? Work equals, you hand wrote it on your sheet, so it should stand out. Yeah. By the way, in real life, instead of how much work, how much rocket fuel energy, but we'd need to know how many joules of energy per liter we were providing in the rocket fuel. But I mentioned to you a few days ago, we were eventually going to calculate how much fuel you need. Well, we're going to calculate how much energy you need. I fibbed a bit. But the transfer would be pretty easy. I just don't know the numbers. Nevada, what word did I underline? Okay, so here's what I want you to imagine. If we're lifting our rocket, here's my, hang on, I can do better than that. Pause the video for 1 second, Mr. Duick. We're lifting this satellite up. Right now on the launch pad, what's its initial velocity right now? 0. We're going to fire it straight up. We are not putting it into orbit. We're just firing it straight up. At the top for a split second, how fast will it be traveling? In other words, if we're lifting, VI and VF are all 0. So the change in KE is 0. A bit later in this lesson, we'll ask how much to put it in orbit. To put it in orbit, you have to lift it up. That's this equation here. But then you have to give it some kinetic energy, the sideways velocity. How do you calculate kinetic energy? A half m. Which V? V orb, the square root of big G, big M over R. And now it's all coming together, okay? That's how much fuel you need to put something in orbit. Actually, that's a fib because we're still ignoring air resistance, which actually plays a huge role when you're going that fast through the atmosphere, but that we don't know how to calculate because it needs calculus. Okay. Anyways, for this question, and only this question, we can do that. The most common mistake on these questions is when I will on your test ask you to put something in orbit. Kids cross out the kinetic energy because we've done it on the first one. This is just lifting it up there, not keeping it up there. And unfortunately, that means they lose a bunch of marks because the kinetic energy was worth 3 marks as well. What's changing anything? So this is going to be PE final minus PE initial. Oh, this is easy, Mr. Duick. This is going to be, I'm making a mistake, don't write this down, MGH final minus MGH. Why can't I use that potential energy? Because we're going cosmic. We have to use the cosmic relative to 0 at infinity potential energy equation. What's that going to be? Our new equation of the day, negative big G, big M, little m over our final minus negative big G, big M, little m over our initial. By the way, we should end up with a positive answer because it will take work to lift something up. We will have to add energy to get it up that high. We're going to get that positive answer from that. All right. Plug and chug. Very complicated plug and chug. You ready? Oh, Julie's stretching out and loosening up. Yeah. No, you should. Here we go. Negative. Big G. Anyone? 6.67. Big M. Since we're around the Earth. By the way, do the little m's cancel here? There's 2 of them. Is there an M in the W there, though? No. And it takes more fuel to put something heavier up there, so they shouldn't cancel. It's way more expensive to put the ISS up there than a little communication satellite. Okay? What is M? I've scrolled down. 1,200, was it? Our final. What's the final radius, the final distance from the center of the Earth of this object? Don't count, just tell me. How would I get it in English? Put your calculators down. Oh, because I said this is a height? So, you know what? Let's write down here 1.2 times 10 to the 7th plus 6.38. Is that what it is? Times 10 to the 6th. Now that's only because I gave you a height. If I had been nice and actually given you the final radius, you wouldn't have to add the radius of the Earth. What's a minus minus the same as? Plus. You ready? ditto mark times ditto mark times ditto mark divided by, what's our initial radius? Put your calculator down. I will turn you loose after this example, but I just want to show you we could. This, by the way, last year when I went on my big calculator rant, it was totally for this unit because I knew this was coming down the pipe. I'm going to type in the first one carefully. Now get your calculators out, but go along with me. Negative 6.67, scientific notation, negative 11 times 5.98, scientific notation 24 times 1200 divided by, I guess I got to put the bottom in brackets, 1.2, scientific notation 7 plus 6.38, scientific notation 6. Is that okay, Linz? And the first expression, negative, works out to, I'm going to carry about 5 sig figs. By the way, you're going to find putting stuff up there almost always is in the 10 to the 9th, 10 to the 10th, or 10 to the 11th range. It's a lot of fuel to send stuff up there, just for the record. I'm going to go negative 2.60413 times 10 to the 10th. I'm going to write that down. Negative 2. What did I say? 60413. And Connor, this is why I yelled at you. No, Duncan, this is why I yelled. No, Robbie, sorry, I knew I yelled. This is why when you started to calculate this number here, I said, no, because now watch. If I backspace, I just got to ditch the negative, yes? And I just got to delete the 1.2, and I've already got the 6.38 sitting there. I've thought about this. If you come up with a shorter, less typing way, let me know. But this is me thinking deeply and saying, how can I do the least amount of typing? And what I really mean is the least amount of potential for a typo. I think it's here. And as long as your calculator lets you backspace and edit, which please God, I hope all your calculators let you do after my rant from last year. This one is going to be positive 7.50218. And now I can go to my final answer. How much work is it taking just to lift this rocket up there? And not keep it up there. It's going to come crashing back down to the ground. That number plus negative 2.60413, scientific notation button 10. Oh, this is also where my love for trying to use the answer button just breaks down, because to try and get all those previous answers is a pain, but I'll carry it to 5 sig figs, 6 sig figs. I'll definitely be accurate to 3 sig figs. And I get 4.898, you know what? 4.90 times 10 to the 10th. Units. Work. Joules. Energy. If you knew the number of joules per liter of rocket fuel, that's how much rocket fuel you need if we ignore air resistance just to get your rocket up there. Not enough to keep it up there. That's just enough to get it up there. Is that okay? So I'm going to pause, Drake. Really, aside from showing you the new equation for cosmic potential energy, I'm going to argue, so far I haven't taught you a single new thing. We've redone the work energy theorem. Work is changing potential and changing kinetic. With a vengeance, yes. Heavy-duty typing, yes. Of course, since this satellite has no kinetic energy, it's going to fall back to the Earth. To lift an object, we only need to give it but to put an object in a stable orbit, we need to give it potential energy and kinetic energy. More rocket fuel. I like example 2. You know what? You're going to have a question like example 2. Oh, you know what? I take that back. Example 2 is too easy. I gave you the orbital speed. On your test, I'm also going to make you calculate the orbital speed. the whole schmear, which I think is going to be example 3. Oh, no. Later. I think I'd do that next lesson. Anyhow. Nevada, coming back to you. What's this question asked me to find? Third word. How much work? No, you're right. How much work? I can't go force times distance because the force is changing. I could find the area under a graph, but even if they gave me a graph, it would be a curve, so I don't like there. I'm using and this is why I spent so much time developing that theorem last year and this year. It really is a more flexible definition of work. The notion that work is equal to the change in potential plus the change in kinetic. Can you all underline the word orbit? What word was underlined in the previous question? Just lift it up. What word did we just underline, Kayla? Orbit. What that really means is this. The change in kinetic energy won't be 0. You're going to need some kinetic energy too. This is complicated enough that I break these up. We're going to find the change in potential energy, get an answer. Write it down to like 5 sig figs. We're going to find the change in kinetic energy, get an answer. Write it down to like 5 sig figs. And then we'll add them together. Liam, what do you want to find first? Change in potential, change in kinetic? Doesn't matter. Pick. Change in potential? Okay. Change in potential. What's change in anything, Liam? Oh, this is easy. MGH final minus MG. No, we're cosmic now. It's going to be negative big G, big M, little m over R final minus negative big G, big M, little m over R initial. Negative big G, 6.67 times 10 to the negative 11. The universal constant of gravitation. Are we around Earth? If it doesn't say, we assume Earth, 5.98 times 10 to the 24th. Mass of the satellite, 925. What's R final? I'm so glad Duncan made that fundamental mistake. Duncan said, is it 2.6 times 10 to the 7th plus 6.38 times 10 to the 6th? That would be if I told you the height or the altitude. But what did I give you? I was nice, and I understand your mistake. You are totally not used to Mr. Dewick being nice, and I completely understand why your first assumption was that I was being a mean jerk, because that is my nature. I get you. So that's not really a sloppy mistake. That's more of a mistake in character. What's Dewick being nice for? But yeah, this time I gave you a radius, so I can just go with 2.6 times 10 to the 7th. In other words, Andy, this time I calculated the altitude and the radius and added them together for you and just gave you that final answer. Minus minus is a plus. Ditto mark times ditto mark times ditto mark divided by, and we're starting out 6.38 times 10 to the 6th. I'm going to type this, you type this on your own, and let's see. I'm going to write each one of these down to 5 or 6 sig figs. Psst, I think the answers will be in the 10 to the 9th, 10 to the 10th, 10 to the 11th range. If they're not, you've messed up. And I guess it goes without saying, because you're reusing your data for the second calculation, you really, Kayla, ramp up your paranoia on that first entry and just make really sure you make no typos the first time you're entering all the data. And if you do that, then it's plug and chug. Complicated, plug and chug, but plug and chug. 5.7829 times 10 to the 10th. What did I say it was? 5.78293. So it's going to be that number, take away 1.41904 times 10 to the 10th, 4.36389. 389. 4.36389. 4.36389. And once I get the change in potential, I tend to put a box around that, because as we get more difficult questions, you still have lots of calculations to go, and it's easy at the end to say, now where the heck was that change in potential energy in my work? So put a box around it. What have we just calculated? Riley, we just calculated how much energy you need to get it up there. Now we're going to calculate how much kinetic energy you need to give it for that tangent orbital velocity to keep it up there. I actually calculated it for you already. You know how much velocity you need? 3,917. I have no problem, and later on we'll get there, not asking you to not giving you the velocity, but saying, oh, by the way, you can find orbital velocity. Gravity is what's pulling you in a circle. And I think you end up with V orb equals the square root of big G big M over R, but I have to derive it. And didn't plug that in. But we're a little nicer. Liam, we just found the change in potential energy. What else do we need to find? What's changing anything? We are going to assume worst case scenario that we're starting at rest. In real life, you're not. Why aren't you? Because the Earth is spinning. In fact, this is why NASA is down in Florida, which aside from Hawaii is about as far south as you can get in the US. The closer you are to the equator, the faster you're spinning in terms of your tangent velocity, the more kinetic energy you have from the Earth. The best place to build a spaceport or a space launch port would be on the equator. Yeah. Oh, and they also launch in the direction of Earth's rotation, which conveniently is also over the Atlantic Ocean, which means if anything goes horribly wrong, they've got a big junkyard to drop stuff in. So if something goes wrong, NASA's stuff ends up in the Atlantic. If something goes right, the Pacific is the junkyard of the of NASA after they've used up all their space probes. It all lands in the Pacific Ocean. Yes? That's a great question. Elon Musk, the reason he's trying to do stuff on ships, put your ship on the equator in the ocean somewhere. Bob's your uncle. You get a whole bunch of extra kinetic energy, way less fuel needed, lowers costs. Does Russia have any locations close to the equator? This was one of Russia's big obstacles in the race to the moon. And even to this day, their spaceships, their rockets, are these massive workhorses because they had to put all of it into rocket fuel. They're not getting much of a boost from the spin of the Earth, which is why, if you look at the Russian rockets, they're just, geez, those are big suckers. They had to be. They had to engineer them that way. Yeah. Is that all right? Great question. So anyways, I know technically the KE equals 0 is wrong. No, we're going to be Superman. We're launching from the North Pole, from our Fortress of Solitude. Okay? No? Oh, okay. But for what it's worth, in real life, yeah. Hey, if you become a billionaire, buy an island near the equator, set up a space station. No. Note to self. A half mv final squared. You know what? Instead of final, if you want to, you could call it v orb squared, because that's really the v that we're talking about. Which m? Little m. What are we getting up to speed? Not the Earth, the satellite. 0.5, 925. What did I say orbital speed was? 3,917? I think I calculated that. I think it's right. I don't think I made that up. Typically, the kinetic energy required is either going to be a 10 to the 10th or a 10 to the 9th. It's a little less kinetic energy than to get it up there. And that's why I said, even though further away from Earth means the satellite travels slower, you burn more fuel getting it up there than you do keeping it up there, so it's not a good trade-off. (7.096 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, sometimes it's a factor of 10 less. 7.096 times 10, 7.096 times 10 to the 9th. If you want to, you can make a little note. V orb will eventually be square root of big G, big M over R. That was what we got last lesson a bunch of times when we said, gravity is what's pulling me in a circle. And we got the V by itself. You don't have to memorize that equation in red. Some of my kids do just for this unit because they get sick of the derivation. I've never memorized, though, the period one or the radius one. I just know that radius requires cube root, and so I'm always smiling when I'm about to show you that one last lesson because, holy smokes, you get to use your cube root. I remember that, but that's just because I'm a nerd. Okay. Nevada, what was this question asking me to find? Well, work. I should have put a box around this answer, too. Is the change in potential plus the change in kinetic. The change in potential was 4.36389 times 10 to the 10th. The change in kinetic was 7.096 times 10 to the 9th. Here it is, boys and girls. How much work is it going to take? How much rocket fuel, how much energy will it take to put this satellite in orbit? Thankfully, I still have this number stored on my calculator, so I just have to go plus 4.36389 times 10 to the 10th, and I get, now I'll go to 3 sig figs. 5.07 times 10 to the 10th. Units, joules. Whew. That was a lot of work. Too soon? Okay. Turn the page! Or is next page over? Turn the page. A missile is launched from the surface of the Earth straight up. In my picture, straight sideways, but, up. Its fuel is used in initial burst, so we're going to talk about right after it's left the launch pad, just to make this a magic physics question. Let's assume right when it leaves the launch pad, that's its maximum kinetic energy because we've burned all the fuel instantly somehow. And then we're going to coast the rest of the way. So as it arises, the only force it experiences is gravity, and we're going to ignore air resistance. As it rises, what happens to the kinetic energy and the orbital potential energy? Well, first of all, as it rises, what happens to its speed? It goes faster? Remember, I said we're firing all of our fuel at once and then coasting the rest of the way. I think it's going to slow down because gravity is tugging it down. Yes? So if its speed is slowing down, what's happening to its kinetic energy? Increasing or decreasing? Kinetic energy is a half mv squared. If v is getting smaller, you guys are, no, kinetic energy, we're doing the first column, kinetic energy, wow. We fire all of our fuel, so we have max kinetic energy right now, boom! And then we coast the rest of the way. What happens to our speed? We slow down. What happens to our kinetic energy? No, yes, yes, yes? What happens to our orbital potential energy? Now, let's be clear. You still have negative orbital energy, potentially, because when do you hit 0? out at infinity. But as you move further from Earth, you're less negative, which means you are increasing. Correct answer? C. Oh, I would love to do escape velocity, but we're going to pause here. Yes? No, this is cool. Yes. Man. I would love to teach you how to build a Death Star. We might get that in. For now, as a start, we'll continue this Monday, but you can do number 1. You can do number 2. 3 you can handle. 4 you can handle. And I'm going to skip 5 and 6, 7. Can I teach you how to build a Death Star? That's the question.